Hello, good afternoon, everybody. Welcome to the session 3053. So I'm Matthew George, and I'm a developer working with the Windows Server group, and I work on the file server and clustering team. So we are the guys who do a lot of the server storage, file sharing, and a lot of the clustering, the clustered file shares and things like that. So this talk is not a very like a developer focused talk in the sense that I'm not going to talk about APIs and so on and so forth, but I'm going to talk at a higher level about a lot of the storage features which are now available on Windows Server 2012 and how you can think of deploying your applications over networked file storage, or NAS as you call it. And I'm specifically going to talk about enterprise applications like SQL and other high performance applications. So all right, let's get going. So this would be the rough outline of the talk. I'm going to talk a little bit about motivation for using shared file storage or NAS, and then look at the overall storage related features on Windows Server 2012. And for those of you who haven't heard much about the SMB3 protocol, I'll talk briefly about the SMB3 protocol and how it helps your applications take advantage of high-speed networks and fault tolerance and things like that. And then how, as an application developer or a storage architect, how you can make use of these features in Windows Server 2012. And then a few programming considerations with respect to how you can extract maximum performance from your network storage subsystem. So this is an introduction. So before we go into the details, let's try to see why network file storage traditionally was never considered interesting in the storage community. Right? There's been a lot of perspective about network storage. It was mostly historical, but things have changed quite a bit. So historically, when you access files stored on a file share or on a network appliance, you could end up thinking about poor performance, partly due to the network and partly due to unreliable storage subsystems and so on. Things were generally considered unreliable in the sense that if the server went down or the network went down, your application would see errors, and then you would have to take corrective action. And networks were also part of the problem. And there was a lack of, integrity guarantees when you run your applications on a network as against local storage. With local storage, you often assume that if you write something to disk, it would be correct and it would be persistent on disk. But when you're talking about network storage, there was this air of unreliability, so to say. And the last aspect of it was diagnosing something which went wrong. When you have a machine and local storage attached to it, analyzing things were much simpler. But in a network world where you have a client and server and possibly more than one client and more than one server, diagnosing and analyzing issues were kind of difficult. Now, when you look at the last 5 or 10 years, the networking technologies have changed so much. They have become extremely fast, reliable, and low cost, especially when compared to direct attached storage. Now you have 10 gigabit Ethernet is becoming quite commonplace, and then you have motherboard chipsets with multiple integrated NICs right on the motherboard itself. So things are reliable, things are low cost, and speeds are now very much comparable to what you would get with like a fiber channel or a direct SAS attachment, especially 10 gigabit Ethernet. And I'll talk briefly about InfiniBand and RDMA, which gives you up to 56 gigabits throughput on a single InfiniBand link. And then there is a whole bunch of changes to the storage backing the file server, in the sense that it's now way more robust and reliable. So you can set up your RAID or parity configurations so that your data is protected, integrity is guaranteed, and you get real good performance. And the other aspect of it is managing this thing. So traditionally, management of block storage is somewhat of a difficult, it's an art, it's a fine art, so to say. So you need a storage architect and SAN architect and so on to manage your block devices, your SANs. But now with file storage, it's very, it's something which most of you are probably familiar with, managing shares on a file server, assigning permissions. You don't have to deal with assigning disks to machines and so on and so forth. It's just setting up a share, assigning permissions, and then you're ready to go. And then you can relocate these shares from one machine to the other, so you can move around things, you can move around your application and storage. So let's take a look at what's new in Windows Server 2012. You might have heard of a lot of these things already. The primary, one of the big focus in the Windows Server 2012 framework has been continuous availability. So we already had clustered file shares and so on in the previous OS releases. But the big change here is that applications running on a client do not any longer see any failures when a cluster node dies and the share or the file server resources get moved from one node to the other. So that's what we call continuous availability. And we also have a scale out file server now, which is an active cluster configuration. So for those of you who are familiar with the old clustered SMB shares, it's active passive in the sense that one node owns the share, and if that node dies, the share and the IP addresses and all the resources move over to the second node, and then the client picks it up. So now we have a scale out setup where you can have a bunch of servers all exposing or all front-ending the same storage and the same shares. So the client can connect to actually any of the nodes and then get access to your share. So those two are protocol, SMB protocol features. Then the third one here is bandwidth aggregation using SMB multi-channel. So if you have multiple network interfaces on your machines, on your clients and servers, now without any additional configuration, if you set up a file share and access the share from a client, your client can actually use the bandwidth available by all the network interfaces. And there's no configuration required for doing this. And we support new network fabrics, the primary one being RDMA capable fabrics, and there are 3 of them. We'll talk about that. And there's a feature called SMB Direct, which allows you to, as an application developer, to take use of that. Then we have encryption. And then on the file system side, on the server, there are a bunch of storage features. So you might have heard about storage spaces, which gives you the ability to define a pool of disks and then carve out volumes and partitions from those pool of disks, and then it gives you resiliency and then fault tolerance and so on and so forth. And then there is a resilient file system, which is the new file system which was developed for Windows Server 2012. It works in conjunction with storage spaces to give you a lot of these resiliency guarantees. And then the other important thing about REFS is that there is no concept of a check disk or checking for corruptions. It will fix things on its own, and it's designed in such a way that corruptions will not arise. It does not, for those of you who are familiar with files, it does not write in place. It always writes, does a copy on write, so to say. So it will never corrupt data. Then there's a whole bunch of manageability and diagnosability improvements, and then a lot of our administration is now PowerShell based. You can pretty much do almost all the configuration and even much more using PowerShell now than compared to using the UI, which is the traditional way of setting things up. So what's a continuously available file server? So the main thing here is that it completely insulates applications from any sort of failure. So server failures and network failures, those are 2 modes of failures which we're interested in. So it gets you to almost local disk like semantics. So when you're running an application against a local disk, you don't generally expect transient failures or intermittent failures. So now with a file server, you can get almost all those guarantees. So you are insulated from network and server failures. So any I/O issued by the application will not come back with an error if there's a failure. So the client, the SMB client, or the redirector in Windows will retry I/O. It will try for a while. So we'll talk about it in detail, but it will retry I/O. It will try multiple network paths, and then it will also handle failures on the server or on the storage side. So as an application developer, if you are a Win32 or .NET, whatever file I/O APIs you're using as an application developer, they will continue to work. You don't really need to do anything special to leverage this. You just need to have Windows Server 2012, or rather Windows 8 on the client and Server 2012 on the server end, and you will automatically get all of these benefits. So this is kind of an illustration of how a continuously available share works. So both the SMB client, which runs over here, and the SMB server, which is the file server, they are both enhanced with the SMB3 protocol. So now they understand all these failure modes, and they actually are able to reestablish your connections on the new node, and then continue your I/O. So all that your application sees is a small I/O delay. That will be in the order of about 5 to 10 seconds typically when a failover occurs. And failover can be unplanned or planned. And you see zero downtime, you see a small I/O delay, and then any file or directory operations which you might be interested in, they will be transparently failed over to the other node. So you don't see any failures. And planned failure is kind of interesting, especially in the cluster. When you have a cluster of file servers, you might want to take down nodes for patching or hardware upgrades and so on and so forth. So you can do like a rolling upgrade cycle. You can take down one node, all the clients will switch to the other nodes, and then patch it up, bring it up, and then in fact, there is automated cluster-aware patching in Server 2012. So in fact, you can it's kind of a task in Server 2012 clustering. You can set it up so that the entire thing is automated. You point it to a set of patches which you want to install and on all your servers, and the system will actually take care of bringing down nodes one by one, upgrading it, patching it, and then bringing it up. So you don't need to actually go to each machine and patch it. There's a whole automated system built into Server 2012. And it allows you to load balance too. So now what this requires is you need to set up the SMB server in a failover cluster. So failover clusters have been available in Windows Server for a while now, but so you need to set up the file server in a failover cluster, and then both the client and the server must implement SMB 3.0, which means that they have to be running Windows 8, Server 2012 or above. And then you have to specially mark the share for what is known as continuous availability. It's a bit which you can set on the share. It's a property which you can set on the share. The other configuration which is now possible is called the scale-out file server. This is an active-active configuration in the sense that the same share, so in this case //fs share, it's the same share which is visible across all nodes in the cluster. And it's accessed via this name fs and the share name as share. Now what backs this behind on the cluster is a cluster file system. And if you are familiar with clustered shared volumes or CSV on Server 2008 R2, this is what we use internally to support a unified namespace. So there is clustered shared volumes running here, and then this is attached to via SAN or direct attached storage to a disk subsystem behind. Now, the big power behind this one is instead of active passive, now you have active active. So client, your load is automatically replicated or rather distributed across all the file servers. Now clients can connect to any node, and clients can be administratively, you can move a client. Let's say a client has connected to a node X here. You can administratively tell that client to actually move to another node for patching or whatever reasons. And this can be planned or unplanned. And the thing to remember about this is that this is primarily designed for server application workloads. So you don't want to use this as a general purpose file server for serving out your documents or whatever. It's mostly for hosting VMs or databases and things like that. So it's purely for server application storage. We'll talk about why it is. The primary problem is that any metadata heavy I/O pattern can cause performance to degrade because there's a whole bunch of coordination that has to happen across nodes. So as long as your data or your I/O pattern is data heavy, this works very well and it scales very well. And this again requires SMB 3.0. And older clients can connect, but you don't get transparent failover. So that's SMB2 clients can connect. And the same thing applies to the previous configuration. Older clients can connect to it, but you don't get the failover guarantees. Now, talking about a feature compatibility, pretty much all of the Win32 APIs which you would normally use to access file shares. So this would include all the .NET APIs too, because they are usually built on top of the Win32 NT APIs. Pretty much all of them will work across standalone SMB, continuously available, and scale out. Now, some of the limitations you can see with respect to hard links. Hard links, for example, don't give you continuous availability. So if you have a file with hard links, you don't get continuous availability. And same thing with alternate data streams. These are not used so much, especially alternate data streams are not extensively used. And then you get symbolic links, though, and then write-through and unbuffered I/O is something which enterprise heavy data applications use a lot of times. So database applications, for example, they use both write-through and unbuffered because they want their data really persisted on disk. So all those work. Transactional I/O, TXF, if you have heard about it, is not supported. Encryption is supported. If you have EFS on your file system, it's supported for the continuously available server. It's not supported for scale out. Any volume level APIs, none of them are supported. And opportunistic locks, this is not a user visible feature, but this is something which the SMB protocol uses internally to cache data. So opportunistic locks are available fully on the active passive setup, but on the scale out setup, it's not fully supported in the sense that you can do read caching. All the nodes can actually cache data, but when you have to modify them, it has to be done on disk. So it's kind of limited in that sense. But for the kind of applications which we're targeting, this is really not a big deal because they're data heavy applications anyway. Now, the next thing I want to come to is multi-channel. So this is all of the previous couple of slides were talking about server failures and how to how does a client handle failures on the server. Now, this is talking about the network aspect of it. So if you have multiple network paths between the client and the server, now we have a new feature called SMB multi-channel, which actually leverages all available network links between the client and the server, and there is no extra additional configuration needed for this. So traditionally, if you have used SMB, when you access the share, the client would use just one interface. It would just establish a single TCP connection or whatever to the server, and then transfer your data using that. But now we can leverage multiple NICs or even use multiple TCP connections on the same NICs. And I'll come to this as to why you would need that. And this is compatible with LBFO, which is the fault tolerance built into the network stack. This kind of work, you don't require LBFO, but it can work in conjunction with load balance, the failover, network level failover. Now, I've shown two setups here. One is with LBFO enabled, and you have two 1 gig E NICs. And then the second is a setup without LBFO, but with two 10 gigabit Ethernet NICs. And it complements. So LBFO is the NIC teaming I was talking about. And the important thing is that now we can aggregate bandwidth over multiple network links and multiple NICs. So and it's completely transparent. So there is no configuration. And there's a whole bunch of PowerShell commands to actually diagnose what's going on and how the setup works. All right. Now, this is a look at CPU usage when you deal with very high throughput NICs. So previously, before multi-channel, let's say, if you were trying to transfer, let's say you have a 10 gigabit NIC on your machine, and you're trying to transfer, do file I/O over the 10 gigabit NIC, we would establish exactly a single TCP connection between the client and the server through one NIC. The other NIC would not even get used. Now, what would happen is that when you're transferring data at that high of a throughput, the interrupt load is directed to exactly one core on the CPU. And this is a feature on the networking stack. So when for a single TCP connection, all interrupts on that connection which occur when packets arrive on the connection are directed at one core or one CPU core. And what would typically happen is that you would saturate one core, and you would not be able to get more throughput even though all your other cores are kind of free. So you would saturate your throughput because of CPU utilization, as well as the fact that you're using just one NIC. Now come to Windows Server 2012. We can now establish more than one TCP connection over the same NIC, as well as make TCP connections over additional NICs. So essentially, you have 4 TCP channels here spread over 2 NICs. Now what happens is that for each TCP connection, the networking stack will distribute your load over all the 4 cores. And essentially what you would see is you would see fairly low CPU utilization on all the cores, and it's low, and you are able to get all the 20 gigabits of throughput. So it's 10 gigabits and 10 gigabits. So you'll get all the 20 gigabits of throughput when you doing multi-channel. And you don't really need two interfaces. You can just do one, and we will do multiple connections over the same interface. And again, the application doesn't need to really do anything to make use of this. You just open a file on a share and then do I/O to it. You'll get all the benefits automatically. Now, this is a very interesting. This is in conjunction with the multi-channel. So I talked about new fabrics, network fabrics, which we support, and other than TCP/IP and Ethernet. So this is the new one, which is called RDMA, Remote Direct Memory Access. I don't know how many of you are familiar with it, but it's a support in the NIC and the switches and the fabric to basically do transfer of data between client and server without any CPU involvement. So it's basically, I'm sure you have heard of RDMA, which is typically used on a local machine. This is RDMA over the network, and it's called remote DMA. And it's extremely low latency in the order of microseconds and very large throughputs. And there are 3 different fabrics, technologies which support RDMA. iWarp is actually RDMA over TCP/IP. So if you don't need any specialized network fabrics, it can run over standard TCP/IP. But obviously, once it runs over TCP/IP, you don't get the 56 gigabits of throughput. Throughput is lower, but the advantage with iWarp is that you can use your existing network fabrics and switch Ethernet switches and whatnot, and it's routable too. So you can actually run iWarp over across data centers and so on. This is again based on Ethernet, and it requires switches, special switches which support this transfer, and then so this is not routable, but you can still use your Ethernet infrastructure. And the last one is InfiniBand, which is a completely new, different fabric. So you need different switches and different cabling and all that, but it gives you the best throughput and the lowest latency. This is actually very popular in the high performance scenarios where, like, people using MPI and message passing interface for high performance applications, they all often use InfiniBand for extremely low latency. So we support all these 3 different types of fabrics, and a NIC which supports this is what we refer to as an RNIC, or a remote DMA capable network interface. Now this is kind of the flow. Again, the important thing to remember here is no changes to the application, no changes to the API. So they just use your Win32 APIs. Now the SMB client on the client machine running the application will decide, if there are multiple interfaces, it will decide whether to use the traditional TCP stack or whether to use the SMB direct, the remote DMA path. And it makes a decision in essence, if it finds a TCP and an SMB direct path, it always prefers SMB direct because it's much lower CPU overhead and much faster. And then there's a layer of thin layer here called the NDKPI, which is basically a very thin interface into the RDMA NIC hardware. We use that interface. This is a public API now. And we use that interface into the RDMA NIC to directly transfer data. So how this works is that when the application, let's say the application is doing, say, a 1 meg write into a file, the SMB client registers the 1 meg buffer and then sends a pointer to that buffer, so to say, a descriptor for that buffer over to the server. And the server directly pulls the data from that buffer in the client to a buffer on the server without any CPU involvement, which that's where the RDMA, the remote DMA portion of it comes. So you can transfer extremely large amounts of data at very low CPU cost from node to node. And it's completely, you just need to do file I/O. You don't really need anything extra in your application, so to say. Now, when you look at it from a higher perspective, as an application developer, how do you get access to all these features which are offered by Server 2012? We have focused big time on two scenarios here. So one is a virtualized application environment. So you run your application within a virtual, a Hyper-V instance on a server, and the Hyper-V, the storage for the VM is actually residing on a remote file share. Now, why I say that these are three different paradigms is basically that we have extensively tested and validated Hyper-V against SMB and SQL against SMB. So these are two. So if you're writing applications on top of SQL, for example, you can actually deploy SQL, and then instead of keeping the database on your local machine, point it to a remote path, and you get pretty much all these guarantees which I talked about earlier. Now, you could, in fact, even run. So for those who are familiar with Server 2012, you can actually mount a VHD natively and then point the VHD to a remote server. So you don't even need Hyper-V. You can actually directly mount a VHD on a network share on a machine and then locally access it like a local volume. And then the third one is UNC-aware apps. So basically, any app which it's a custom app which accesses local storage, you can directly point it to UNC storage, and it will continue to work without changes. So we look at these scenarios, how things work, and then the last one I'll talk about it in a little bit more detail as to what APIs you can use and so on and so forth. Now, Hyper-V, as I said, completely supports hosting virtual disks and the Hyper-V configuration on a remote server. So you can set up a continuously available file share, host your Hyper-V configuration and your VHD on the file server, and run your app within the Hyper-V instance. Now, it automatically gets you all the benefits of multi-channel and continuously available SMB. Now, you could also get other additional benefits. So you can migrate your storage. So you can, for example, you can start over with your Hyper-V VHD on your local disk, and then while your VM is running, you can migrate the storage over to the remote node, to remote file server, without even interrupting your workload. Your Hyper-V, your VM continues to run, but you can migrate your storage between two nodes, or between local and remote, or from remote to local. Any of the combinations will work. And you could, this is migrating the storage of the Hyper-V, and the other one is migrating the VM itself. So that's a client side. So you can move the VM from one node to the other, and everything while it's running. And again, since your app is completely virtualized and it's running inside the VM, you don't actually see any interruption. You don't need any changes to your app. It continues to see a local drive within the Hyper-V, and then it continues to run as normal. You don't see any interruptions. So this is the stack. So you have the guest or the Hyper-V instance. The application sees a local disk, a SCSI disk or a local volume, and then this is redirected through the SMB client through your NIC and onto the server. So it's completely transparent to you, and your app, as far as your app is concerned, it's just local storage on your Hyper-V instance, on your VM. Now this is trying to illustrate how easy this is to set up. So all you need to do is provision a file share. So you have to set up permissions, for example. So for running Hyper-V against a remote file share, you need to grant permissions to the machine account, which is what I indicate here by the HV1 account. So if you're running your client, your Hyper-V instance is running on this machine called HV1, that machine will access your file share in the context of the machine account, which is this domain/HV1 user. So you grant permissions to that, you grant permissions to the admin. Now, this is illustrating the new PowerShell feature for creating your file share. So you create a file share pointing to that path and granting permissions to these accounts. And then all you need to do is create a new VHD, again using PowerShell. You can you just point to the remote path and give the size of the VHD and so on and so forth, and then create a new virtual machine pointing to the VHD which you just created before. And this path is actually used to store the Hyper-V virtual machine configuration. So the configuration along with the VHD, they are all stored on the remote server, and then that's how you would create a virtual machine instance, and then you set it up and then run your application. And there are a whole set of things you can do here. You can use differencing disks and so on. So you can have a single logical image which you can assign to multiple Hyper-Vs and then create difference disks so that they all work off the same base image, for example. Now this is a standalone setup of Hyper-V. So you have multiple Hyper-V hosts and VMs running there, and you have a single file server with a share which is backed by storage spaces. So it basically takes a pool of disks and then converts it into volumes. Now the great thing here is the simplicity. So once you set up your file server with your disks, all you need to do is, as I showed before, provision your share and get access. And the storage here can be made fault tolerant by using the storage spaces features like parity or mirroring and so on and so forth. So you can do RAID-like configurations on your storage. So your file server is resilient to, your storage is fault tolerant because you're having storage spaces here. It's low cost because you don't really need any additional technologies or any special fabrics and so on and so forth. And the main limitation here is if the file server dies, well, your VMs also die because it can't access its storage. So that's the limitation here. But this will work for almost all the cases where you're not worried about the file server dying, so to say. But you get all the network resilience features because of multi-channel right here without any additional setup. Now this is the other setup. This is a more fault-tolerant setup. So you can cluster both the Hyper-V side as well as the file server side. So by clustering the file server end, now you are making your setup resilient to failure of one or more file server nodes. So if this node dies, all your shares are moved over here, or if it's a scale-out share, the client will actually go and access another node. And on the Hyper-V side, if you cluster the Hyper-V side, and these are separately clusterable, so you don't necessarily need to do both. You can just do one end depending on what kind of scenario you're interested in. If you cluster the Hyper-V end, if one of the Hyper-V hosts dies, your VM will automatically get restarted on another node by Hyper-V. So you get the benefit of clustering in both the client end and the server end. So the VMs are highly available, file server is continuously available, and the storage is also fault tolerant. So this is like the best possible setup which you can have. Now let's come to SQL Server. Now with SQL Server 2008 R2, we formalized support for storing databases on SMB shares. So it's no longer, they have tested it, validated it, so you can, there used to be, for those who are familiar with SQL, there used to be a special trace flag which you had to set. It's like a debug flag which you had to set if you want to run SQL over SMB. That's no longer required. And both SMB 2.1, that means you can do this on Server 2008 R2 as well as Server 2012. It's fully tested and supported. Now with Server 2008, SQL Server 2012, now we have the advantage of SMB 3.0. So you get continuous availability in addition to all the features which were supported in SQL Server 2008 R2. So you could set up a cluster with continuous availability, and then you can point to, you don't need to have the drive letter, because this has been a consistent problem when you host a lot of disks, or when you access a lot of storage. The 26 drive letter limitation becomes a problem. So now you can straight away access your UNC paths, and you can even host your root, DB root, on SMB file shares. And the system DB and all your databases can be on file shares now. It's officially supported. And I'm not going to talk about it much, but again, this is hosting Hyper-V, your database and your logs. So typically, just like you would use local disks, you would set up separate shares for your log and your primary database, and then you could host it on a file server, and your applications running on top of SQL Server would not see any difference whatsoever. So this is a failover scenario. So you would do a normal operation, something fails over, the SMB client here moves to the other node and then continues its I/O. This is again setting up. This is similar to the Hyper-V setup. So you grant your permissions, create the share, and then when you create a database in SQL, just point to the UNC share. That's pretty much what you need to do. Now let's come to the third one, which is direct access to shared file storage. This is the case where you have a custom app which works on the local disk, and you want to move to using network file storage. So the way you do this is, the recommended way to do this is via UNC path. So instead of a local drive, now you access server share, you set up your application to access a UNC path, and this will go through the SMB redirector, and you get pretty much all the benefits I talked about earlier. The only additional step you might need to do here is to set up credentials. So if you are in a domain infrastructure where your user has permissions, you probably won't need to do this. But if you are not, then you have to set up explicit credentials so that you can go and access the UNC share. You don't need to do this on a local disk. So you can do this via two means. One is via the credential manager, which is there on all Windows setups. So there's a UI available to do that. You can set it up such that you can say use these credentials when talking to the server. Or you can do the net use equivalent. You can map a drive and then run against a drive. The thing is, you need to explicitly provision your shares. Depending on the application, you need to provision your shares for continuous availability, scale out access, encryption. These are things which you need to do as a one-time configuration step. Now, the basic theme with respect to your applications is what is called continuously available file handles. So those who are familiar with Windows Win32 or .NET, right? So you open a file and you get a file handle or a stream handle or whatever, and this handle is continuously available in the sense that once you issue I/O on the handle, the SMB client will make sure that the I/O happens on the server. It will not return an error due to any intermittent network failure. So you get consistency. If you do a read or a write, you are ensured that the data is persisted on disk. And if a connection is lost in the middle of a transfer, we will automatically reestablish the connection, or we will replay the I/O on using a different channel. It's completely hidden to applications. Now, if the server doesn't come back, or no path to the server is available for a while, then we start failing I/O, because you don't want your I/Os to get stuck indefinitely. So we use the default 60-second timeout, which has been traditionally the default SMB timeout. So we will try up to 60 seconds, and this is configurable again, to see whether the server is available or the network is available, and then if it isn't, we will fail the I/O and the file handle is actually lost. And once the handle is lost, the application will see error. So until the timeout, we will retry I/O, we will replay the I/O, and then make sure that all the data is persisted to disk. Now, even all operations like which you can think of on a file system, like creating a new file, deletion, rename, they are all atomic, and you will not have inconsistencies if a failure occurs in the middle of a rename, for example. It's guaranteed to succeed. File extension. So any metadata changes will be persisted. They are logged and persisted and recovered on the new node. Now, for directory operations like doing a dir, enumerating a directory, it's a best effort guarantee. So there is no hard guarantee there, but it's a best effort guarantee. We will try retrying the operations, but it's not a hard guarantee like what you have on file handles. These are all hard guarantees for 60 seconds, but this is a best effort guarantee. And the reason for that is there's a cost involved in giving you resilient or persistent file handles, so to say, continuously available file handles, and then we want to kind of mitigate the cost for lower priority or lower resiliency operations. So directory operations are best effort, and but it will work in almost all the cases that I have seen. Now, what is the cost of doing this? So you could think, hey, I would just put continuously available, I'll mark all shares as continuously availability, but it comes at a cost. And the primary cost is with respect to persisting all your data on disk. So the file server operates in a write-through mode. So if you have disk caches and so on, it will speed up. But effectively, what is happening here is once the client writes some data, let's say, to the server, the data has to be persisted to disk, so that even if it fails, if the server fails and the share is brought up on another node, the data is not lost. So it operates in write-through mode, which means a lot more I/Os than what you would expect on a normal file server. And then you need disk subsystems which honor the write-through flag. And a lot of the IDE SATA disks, a lot of them don't honor write-through. So you need a good storage subsystem which honors write-through so that this works correctly. And then there is a bunch of additional disk I/O to track any file handle state which needs to be recovered when the handle fails over to the new node. So there's state associated with file handles and state associated with metadata changes. So these things are tracked on disk, so they result in additional I/Os. But as long as your application is data-heavy applications, these I/Os would generally be minimal. If you're talking about an app which is modifying and creating a lot of new files, renaming and deleting files and so on, this aspect of it gets heavy, which is why we recommend that all these setups be used mostly for very data-heavy workloads or enterprise workloads. So these kind of apps will work very well. So apps which use long-lived file handles. So you open a handle, keep the handle open for hours together or days together and do a whole bunch of I/O works very well, and very intensive I/O. And metadata intensive apps don't work too well, or there's a cost associated with it. So you want to make sure that your app falls into like a data-heavy category. But again, if you're running on top of SQL or Hyper-V, these things are hidden because it's Hyper-V and SQL which is actually using the features of SMB. So you're building SharePoint apps or apps on top of SQL, you don't really need to worry about these things. Now, should apps, if you're writing a native app, should apps really care about continuous availability, or does it need to be aware of it? For most purposes, you don't need to be aware of it. It's automatic. But in case, let's say you're a database app or something, and you're writing a database or a high-performance app, you want to make sure that the file handles below you are continuously available. There's a way to query it, and it can be done in Windows. I've illustrated the Win32 API, get file information by handle, and you can query for this file remote protocol information, and it has a bit which says the handle is persistent. So if you want to explicitly query for persistent handles and the kind of guarantees which offer, you can actually query for this, but and maybe log a warning or something. I believe if you set up SQL or Hyper-V against SMB share, it actually does this, and then it will log a warning saying that, hey, you might be using a file server which is not continuously available, and then, but it will still allow you to do it, but it logs a warning. So you can do this in your application. Now, the second interesting aspect of this is when you talk about continuous availability, the server, in order that failovers can happen correctly, or in order to give you fault tolerance, the server actually reserves the handle or keeps the handle for the client to come back and reclaim it when a failover happens. So the consequence of this is that if, let's say, you have a clustered client. So clustered client is a scenario where the client application is clustered, so it can move over from one node to the other. So when you have such an application, when a client node dies, your application instance will move to another node. Application will get restarted, and it will try to access the file. Now, the problem is that the server is actually holding the handle, thinking that the client which died is going to come back, but it doesn't. So it denies access to the new instance of the client from accessing the handle. So to prevent this, what we have done is a client app can register an app instance. It's some kind of an ID for the app, saying that all file handles associated with this application are tagged with this app instance ID. So when the server detects the same application, so when the client gets restarted on another node, it uses the same application ID, app instance ID. Now the server actually looks at it and then says, hey, this is another instance of the application which got restarted on another node. Let me abandon all the IOs and all the handles which were owned by this application from the previous node. So it discards all that state and allows the application to reconnect back to the file and then continue on. So this actually is used by Hyper-V and clustered SQL. So when a SQL instance fails from one node to the other, it actually uses the application instance ID so that it can get back access to its database. And this is the API which is available. It's a user mode API, part of Win32. It's there on MSDN. But if you are writing a clustered app directly, you would use this API to get the behavior which you want. And this is for driver writers. If you are a driver which, for whatever reason, you want to add an app instance ID, you can attach a create context. This is an extended create parameter, which is not available to user mode applications, but drivers can actually use this. But for user mode applications, this is the primary way by which you do this. And by doing this, all handles opened by this application or its child applications, depending on whether this flag is set, will be tagged appropriately, and the server will do the right thing. Now, the last thing I kind of want to talk about is how to achieve very high I/O throughput in your applications. Now, I want to classify I/O into two categories, large I/Os and small I/Os. So large I/Os, the metric you are interested in is bytes per second, or megabytes per second, or gigabytes per second. It's the throughput, the raw throughput, which you are mostly interested in. This is not too hard to achieve. So as long as you issue large I/Os, and you issue them asynchronously and then pipeline them. So you issue 10 of them or 16 of them, depending on what kind of throughput you want. It's fairly easy to achieve that. And the CPU cost for this is much lower than the small I/O case, because it results in fewer passes through the file system stack, fewer network I/Os, and fewer, basically larger disk I/Os too. So this is not too hard to achieve. And very often, people who do large I/O, it's often sequential, like your database logs and things like that are sequential in nature. So disks also do very well on large I/Os. So your file copy or database logs are examples of large I/O. And this is fairly easy to achieve with low CPU utilization. Now, when you come to small I/Os, that's when things get much more difficult. Here the metric you're interested in is not really megabytes per second or bytes per second. It's the number of IOs per second which you can achieve. And this becomes CPU intensive because when you are talking about 4 kilobyte IOs, for each 4K you have a full pass through the stack. You have to go through the SMB redirector and then through the network stack and the server and the disk and so on. And they often tend to be random IO too. So all the more worse in the sense of performance. This is a much harder problem to deal with when compared to this one. Now, to the key to achieving high IOs per second or high throughput is to talk about caching. So caching, when you're talking about remote file systems or remote file access, caching can happen either on the client or on the server. There's caches on both ends of the pipe, so to say. So you have to be very aware of what benefits caching can give you, as well as what are the limitations. Now, caching helps absorb bursts of I/O for a short period of time, because if you have an app which generates, let's say, 10,000 IOs in a second, and it's not, and as long as all the I/O can fit into the cache, it absorbs or it smooths out the I/O rate. That's what it gives you. But when you're talking about sustained network traffic, caching can actually hurt quite a bit. Now, the biggest thing with caching is that it effectively makes read files and write file calls. Even though you think you open the file handle for asynchronous I/O, the moment you start caching, it actually becomes synchronous for the most part, because caching involves faulting in pages and so on. So they're all blocking things which happen inside the kernel. So even though you might think that it's asynchronous, but it actually consumes a thread has to wait for the fault, the page fault to be resolved, and so on and so forth. So effectively it makes the call synchronous, and by doing that you lose your pipeline, your I/O pipeline, because it happens one after the other. And the other aspect of it is you can't get zero copy. So you have an application buffer, you issue a write file, somebody has to copy the data into the cache, and then the contents of the cache is actually transferred to the server. So there is at least one data copy involved in cached I/O. So you don't get zero copy. Now, how do you decide on what to do, or what are the options available? So the easiest option here is to open the file with this flag, file no intermediate buffering. And what this does is disables caching both on the client and also on the server. So now your I/O goes directly from your application buffer directly to the disk on the server. It does not get cached anywhere. That's kind of fairly heavyweight, especially because your reads now will have to come from disk all the time, even though, let's say you have a server which 10 clients are accessing there. Let's say they're all reading the same data. Now all those reads will now have to come from the disk, and that's kind of costly on the server end. But on the client end, it's good because you get full network throughput. Now the second option, this is actually used by, for example, by Copyfile. If you use the Copyfile API or use the Xcopy tool or whatever on Windows, it actually uses this. So this is a way by which you open the file cached, but then you disable caching on the client end only. So on the server side it's cached, but on the client end it's non-cached. So that gives you some of the benefits, because on the server end, typically you have lots of memory, fast disks, and so on. So it can cache a lot more data than what a client can do. So it gives you the benefit of caching on the server. Now the client can completely do pipelined asynchronous I/O on the client, because there is no page faulting and so on the client. But on the server end, it can cache data, and then server actually might be able to do zero copy even when it's cached. So what happens here is that when you issue cached I/O on the server can work in a mode where it can go get a bunch of pages from the cache manager on the server, and then pass those buffers directly down to the network stack, and the network stack directly copies data into the cache pages. So there's no there may not be copy, like CPU based copy involved there. So you can get zero copy, and then large memory resources on the server can usually absorb a bunch of I/O, so you can smooth out things. And the key is to fill the network pipe and to fill the disk queue as much as you can. So typically, when you're talking about high throughput applications, you are talking about doing async I/O. That's where most of the high throughput applications do asynchronous I/O. And the other important thing is things like SQL and Hyper-V and all that. The workloads are primarily non-cached because they have to guarantee or they are written through to disk because they have to. There's a bunch of transactional semantics to be enforced. SQL databases, for example, the log writes have to go in specific orders and so on. So caching actually hurts there. Now, this is an interesting question which we asked. How many IOs can you push with SMB with all these features we talked about? Now, is having a fast enough network and disk sufficient? Well, it turns out that it's a little bit harder than that, especially pushing small IOs. It's mostly about managing your CPU utilization because small IOs tend to generate a lot of CPU, and it's trying to keep the CPU utilization down. And in this context, I want to talk a little bit about NUMA awareness. I'm sure at least some of you know what NUMA is. It's non-uniform memory access, which is basically on a server or a machine with multiple physical CPUs on it or processors on it. There is affinity between memory and processors. So some memory is cheap to access for some processors, while some memory is more expensive to access. And especially each processor has its own cache. So maintaining cache coherency is also expensive. Now, the cost of memory, that's what I talked about. Cost of memory access is based on which physical CPU or processor your code is running on. Now, as an application developer, you need to partition your IOs, so to say, on a per CPU boundary. Otherwise, if you try to reuse the same buffers across multiple CPUs, it results in a lot of cache thrashing inside the CPU, and it kills your CPU performance. Now, typically how SQL does is SQL, for example, has dedicated threads for each CPU which does I/O and dedicated buffers for each CPU. And this is something which you have to do as an app writer if you want to achieve high throughput. Now, the OS and the SMB redirector, we redid a whole bunch of things. We broke down logs. We built in NUMA awareness and CPU awareness into the stack. So once the application does the right thing, the stack and the OS actually will also do the right thing to make sure that your IOs issued on a certain CPU, for example, is always sent via a specific network link. If let's say you have two network links and two CPUs, each TCP connection or each link is affinitized to one CPU. So if that CPU, if your app running on that CPU sends an IO down, we'll make sure that it's sent out on the right network interface. We won't mix interfaces for the matter. So the stack does a bunch of things. So as an application writer, that's what you need to be aware of. Now, this is the last performance numbers which we got before Windows Server 2012 RTM. This is taken on RTM, and these are the numbers which are able to achieve with the kind of networks that we talked about and the kind of disks supporting. This is an experiment to kind of see how far we can go. The first one is large IOs. That's 512 AB, 512 kilobytes, fully read. 2 threads and 8. So 2T is 2 threads issuing IOs, and then 8 outstanding IOs on. So 8 asynchronous IOs on each thread. And the bandwidth you can achieve is pretty incredible, 16 gigabytes per second. Again, so you have 48 Intel SSDs, and I believe it was RAID 1.0. I'm not sure, but I can check out on that. So it's a real configuration, so to say, a real-life configuration. Can achieve about 16 gigabytes per second. And you can see the CPU utilization here is fairly small, even when you're pushing 16 gigabytes. Because of the RDMA, you have 3 RDMA NICs. And to transfer all this data, you don't need the CPU involved at all. So you're getting fairly low CPU and 2 millisecond latencies for every I/O. This is fairly enormous throughput. So this is a database. Well, this is a read. Writes are also fairly the same. They are about equivalent here. Now, the second one is more interesting, which is 8 kilobyte IOs, which is the typical size when you run a database workload, for example. So, the page size 4 KB and 8 KB are 8 KB is more common than 4 KB kilobytes, I think. Again, 100% read for simplicity, and 16 threads and 2 outstanding IOs per thread. This is about 500,000 IOs per second, which you can sustain, 500,000 IOPS. But the bandwidth clearly is low because IOs are small size. The bandwidth is really not very interesting, but we are able to sustain about 500,000 IOPS against a disk. And as I said, I mentioned briefly before, perf counters are now available for pretty much all for diagnosing this kind of stuff. So per share, if you look at the client perfmon, perf counters, you have per share counters which actually show you bytes per second and the queue lengths and so on and so forth. So these are all available for diagnostic purposes, and these are available per share. For each share you are connected to, you get separate counters for on the client. And here you can see, now here you can see the CPU utilization is much higher, and partly due to the stack as well as the application itself, because SQL I/O is also at fairly heavy load trying to generate the reads and so on. So fairly high. This is probably not a realistic. When you run a real SQL workload, you don't get anywhere near this kind of IOPS. But this is pushing it, and you still have half the machine available for you to run your actual workload. And you can see here the latency is also fairly small, still about 1 millisecond. And here are the details on this LSI adapters, and then these are the latest Mellanox InfiniBand cards on PCI 3 8x slots. So they are the latest Mellanox IB cards you can get, and they each support 56 gigabits of throughput on each link. Well, that's pretty much what I have. So the main takeaway I want from this talk is that as application vendors, think of this as a new paradigm where you can access your storage on remote file server. You don't need to necessarily make any changes to your application. Everything should continue to work as it used to. But when you are deploying storage, when you are deploying your applications, think of this as a new way to deploy things, either virtualized applications or SQL or your native applications. They are all available in Windows Server 2012. And Hyper-V and SQL, the two scenarios have been extensively validated and tested because they are scenarios which we can test very easily rather than testing custom applications, right? So these are scenarios which are validated. So as long as you're running on top of Hyper-V or SQL, things are covered, well tested, and supported. And you don't need to make too many changes to your application. And so go build, and that's the end of my talk. So if you have questions, I'll be happy to take them here or outside. Yes? Uh-huh. The question is what happens when a failover happens. So I didn't talk about the internals of SMB specifically, but I can give you a brief illustration of what happens. So all your file handles, the server keeps all state associated with the handle. It reserves it for a particular client. So when a connection drops, let's say all the connections from the client to the server dropped. It's not just a single path failed. Everything dropped. So all in-flight IOs will actually fail to the SMB client because the connection got dropped. Now the SMB client, so if it's active passive setup, everything including the IP address and the share and so on will move to the new node. So we will reestablish a connection to the new node which now hosts the share and the IP address. We will do the usual authentication and connecting to the share and all that, so on and so forth. And then we'll reissue these IOs which were in flight and which failed on the first node. And there is a bunch of ordering guarantees which you have to maintain, but all that is covered in the actual protocol. So we will make sure that writes and writes don't race and so on. So there are a bunch of consistency, data ordering and consistency issues which are taken care of by the SMB client. We will replay those IOs, and then once it succeeds on the new node, we will return success back to the client.
So the client will just use slight delay, that's it, right? Well, no, I'm thinking more like the client does IO, and it hasn't gotten to the next level.
Okay.
The next level can't retry it because it doesn't have it yet, but the client thought he did.
Oh,
How it gets picked up.
the question is, how does the server pick up the lost writes? So it's completely the responsibility of the SMB client to replay it. The server does not keep track of IOs, so to say.
Well, I was thinking the app server, not the SMB.
I see, the application server. The application server will not see any sort of error. So that kind of ties into your question. Does the application server or the application see any sort of failures? No, it does not see anything. It will just see a brief pause in the IOs while the failover is happening, and then everything just resumes. So you don't even realize that something has happened underneath you.
But if he issued a system call,
Uh-huh.
an IO,
Mm-hmm.
the SMB didn't process it, SMB can't retry it.
The question is, if the application issued a system call and SMB did not process. So do you mean to ask that the client itself died?
Yes.
Oh, the client died means your application instance itself died, right?
Well, the client's system died, and then he's going to fall over.
Oh, so this is the case. So you're talking about the case when the application fails over. So that depends on how you write your client application, right? So if your application, the way most apps are written is that if the application fails over, it's up to the application to recover whatever state it needs to do. Like SQL, for example, if a SQL instance fails over from one node, this is not the failure of the file server, but the SQL instance itself. It has to do its own. This is mostly talking about the failure of the file server. So the
Oh, but I mean, if you're talking, the thing is, SQL Server's got commit points and things like that, so you can
Correct.
roll things back. But
Ye-
the average application doesn't. So to really use this, does an application have to be written more like SQL Server to really use this?
if the question is, does an application have to be written like SQL Server to get client-side application failover? I would say yes, but the point is, the assumption here is that for most purposes, it's the failure of the file server which we are interested in, and it's not really the failure of the application, because handling failures in application is an application thing, right? The Windows server dies and it takes down the application with it. Now, if your application is clustered, it's written as a clustered application, the clustering will bring up the instance of the application on the new node, and it's completely up to the application to do its recovery. System is not going to do any recovery for you. Yes? The question is, when do I use iSCSI, when do I use SMB file share? So iSCSI is a block access technology. You can, in fact, use it in conjunction with SMB or separately. The whole point here is that it's much easier to provision an SMB share rather than to provision a block device. And the other part of the block device is there is no sharing. iSCSI target is, for the most part, is exclusively dedicated to one client, and you have to set up permissions. And then the other part of it, at least our iSCSI stack implementation don't support like multi-channel and RDMA and so on and so forth. So in a SQL Server 2012 implementation, is there a reason to use iSCSI? I would say that this is a much more better approach to doing SQL now that we have all these features in the stack compared to doing iSCSI block devices. There is absolutely no loss of resilience. In fact, the resiliency guarantees here are probably stronger than the iSCSI one, because you have network failover also in addition to, and the throughput is also way better right now. Any other questions? Thank you, folks. And if you have questions, I will be outside.